Hello everyone, I am Dr. VRAO. From the lecture 57 of thermodynamics, we came to know that internal energy is the energy stored in a system at a constant temperature and pressure, and moreover heat absorbed at a constant volume is equal to internal energy change. That is, heat absorbed at a constant volume is equal to change in internal energy, right? But most of the chemical reactions are not carried out at a constant volume, right? I repeat, most of the chemical reactions are not carried out at constant volume. That is, in most of the chemical reactions, volume undergoes changes. Volume undergoes change. So, in the reactions in which volume change takes place, heat absorbed accompanying volume changes not equal to or does not equal to the change in internal energy, right? Heat absorbed, that the reactions which are taking place or the reactions are heat absorbed at a constant volume accompanying heat absorbed at a constant volume is equal to change in internal energy. That is from we came to know that from lecture 57, but most of the chemical reactions are carried not carried at a constant volume, because most of the chemical reactions volume undergoes changes. So, the reactions in which volume undergoes changes, heat absorbed under change in volume is not equal to internal energy, right? For example, reactions in open vessels, open flasks, or reactions in test tubes. These are the reactions. For example, if you carried out the reactions in open flasks or test tubes, those are accompanying in change in volume. So, for such reactions, heat Q is not equal to change in internal energy, that is, heat absorbed is not equal to change in internal energy, and in such cases energy changes accompanying volume changes. In such cases, that is, in case of open flasks or test tubes, in such cases energy changes accompanying volume changes, and in such cases energy changes not equal to the change in internal energy. So, in nutshell, in reactions which are carried out in open flasks or in test tubes, there is a need to introduce another function, that is enthalpy. That is enthalpy. That is, which is represented by a letter H, right? Why we are introduced this enthalpy? Because in case of open vessels or in case of test tubes, for example, reactions, if the reactions are carried out in open vessels or in test tubes, in such reactions, in such cases, volume undergoes changes. So, in such cases, volume energy changes accompanying volume changes not equal to that, energy changes are not equal to internal energy change, that is delta U. So, in order to study the energy changes of the chemical reactions in which volume changes takes place, we need another function, that is enthalpy. Enthalpy is defined as enthalpy is a sum of internal energy and pressure volume energy. That is, enthalpy H is a sum of internal energy plus pressure volume energy, pressure volume energy. So, usually heat absorbed at a constant volume is equal to change in internal energy, but most of the chemical reactions are not carried out at constant volume. So, the reactions which are carried out in open vessels or in test tubes, there occurs volume changes. So, in such cases energy changes undergo volume changes, and in such cases energy change is not equal to internal energy, and we need another function, that is enthalpy, and enthalpy is a sum of internal energy and pressure volume energy, and moreover enthalpy is defined as heat content of the system, heat content of the system, right. And coming to the internal energy, enthalpy is also a state function and extensive property. It depends on quantity of matter and chemical nature, temperature and pressure, right. So, it is a state, as the enthalpy being a state function, we cannot determine the exact value of enthalpy. We can measure the enthalpy change for a particular reaction. So, for example, if you take a chemical reaction A to B, if you take a chemical reaction A to B, for this we can write enthalpy change, and for this we can calculate or we can measure enthalpy change, not exact value of the enthalpy, because enthalpy is a state function. So, state function means which depends on initial and final states of the system. So, for this chemical reaction we can write change in enthalpy delta H is equal to enthalpy in the state B minus enthalpy in a state A. In the state A. So, enthalpy, where Hb is the enthalpy in the state B and Ha is the enthalpy in state A, that is nothing but enthalpy of products minus enthalpy of reactants. Okay. So, delta H is equal to Hb minus Ha. Okay. So, for this we can calculate enthalpy change, that is delta H is equal to you just you can write the enthalpy equation with the changes, that is delta H is equal to delta U plus delta PV, right. And in the next step delta H is equal to delta U plus it is you differentiation, that is P delta V plus V delta P. Okay. So, in one case we kept pressure is constant. If pressure is constant, volume undergoes changes. If volume is constant, pressure undergoes changes. But most of the reactions are carried out atmospheric pressure. That is, pressure is constant. Most of the reactions are carried out at constant pressure, that is atmospheric pressure. But most of the reactions are not carried out at constant volume. So, most of the reactions are carried out at constant pressure. So, pressure is constant, then delta P is equal to 0. If P is constant, that is pressure is constant, then delta P is equal to 0. Therefore, we can write delta H is equal to delta U plus P delta V. P delta V, right. So, delta H is equal to delta U plus P delta V, right. And from the first law of thermodynamics, we came to know that delta U is equal to Q plus W. Delta U is equal to Q plus W, right. And if work is done by the system, and that work can be written as minus P delta V. If work is done by the system, that work is written as P delta V. That is, if work done by the, already I told you in the entire thermodynamics, W is work. Work is in the entire thermodynamics, that work is pressure volume work. If if that work is done by this system, then we can write minus P delta V. If work is done on this system, we can write P delta V. So we can write Q minus P delta V. So substitute this value in this equation, that is delta H is equal to Q minus P delta V plus P delta V plus P delta V. So work done by the system, and that is minus P delta V and plus P delta V getting cancelled, and this reaction is carried out at constant pressure, because we kept pressure as constant. We kept a pressure constant, that is QP, that is heat absorbed at constant pressure, is equal to delta H, right. Heat absorbed at constant pressure is equal to delta H. Okay, but heat absorbed at constant volume is equal to delta U, right. So from this we can conclude that from the lecture 57, heat absorbed at a constant volume, that is this, heat absorbed at a constant volume is equal to change in internal energy, and heat absorbed at a constant pressure is equal to change in enthalpy, and this is applicable for this holds good, that is heat absorbed at a constant pressure is equal to change in enthalpy for reactions which are carried out not at the constant volume, that is reactions which are carried or reactions which are accompanying volume changes, then in such cases are reactions which are carried out at constant pressure, heat absorbed at constant pressure is equal to enthalpy delta H, that is heat absorbed at constant pressure is equal to delta H, right. So these two are very important. Heat absorbed at constant pressure is equal to enthalpy change, and heat absorbed at constant volume is equal to change in internal energy, right. Therefore, and there is a relation between internal energy and change in internal energy and change in enthalpy by equation, that is okay. So relation between delta H and delta U, relation between delta H and delta U. Okay. So actually the difference between delta H and delta U is insignificant in case of solids and liquids. In case of solids and liquids, where volume changes are not significant. So change in difference in enthalpy change and internal energy change is insignificant in case of solids and liquids, but in case of gases the difference in internal energy change and internal energy enthalpy change is significant in case of gaseous reactions, and for that we can in gaseous reactions that two are related by equation delta H is equal to delta U plus for example, let us derive this equation. For example, delta H and delta U difference is insignificant in case of solids and liquids, but in case of gases difference between delta H and delta U is significant. For example, for gaseous reactions we can write gases ideal gas equation PV is equal to nRT. PV is equal to nRT. So what is the relation that we obtained from the previous derivation? Delta H is equal to delta U plus delta H is equal to, that is QP. Okay, so delta H is equal to delta U plus P delta V. So for gaseous reactions, PV is equal to the ideal gas equation, PV is equal to nRT. We can write P delta V. If you write P delta V, and you can write delta nRT. That is, in case of gaseous reactions, volume change takes place. Volume change takes place in terms of number of moles of products and number of moles of reactants, right? Number of moles of reactants. So delta Ng, where delta Ng, that is change in number of moles of gases. This is number of moles of reactants or number of moles of gaseous products minus number of moles of gaseous reactants. So in case of gaseous reactions, we can write the for gases we can write the ideal gas equation PV is equal to nRT, and to substitute this value P delta V, I write this equation P delta V is equal to delta NGRT, right. So we can write delta H is equal to delta U plus P delta V. In case of P delta V, we can write delta nRT, delta Ng RT, where delta Ng is number of moles of gaseous products minus number of moles of gaseous reactants. This is the very important relation. Okay, by this relation we can convert delta H into delta U and delta U into delta H. This happens only in the case of gaseous reactions, because in case of solids and liquids, that delta H and delta U are equal, right, and delta H and delta U are identical. Delta H and delta, even in case of gaseous reactions, delta H and delta U are identical if delta Ng, that is number of moles of gaseous reactants or number of moles of gaseous products minus number of moles of gaseous reactants is 0, then delta H is equal to, if delta Ng is 0, if delta Ng is 0, what happens to this equation? Delta H is equal to delta U. So in case of gaseous reactions also, there is a possibility to equate the delta H and delta U, for if provided if delta Ng is equal to 0, delta Ng is equal to 0. Right, and delta, already I told you delta H is equal to delta U in case of solids or liquids. For example, liquid, for example NaCl aqueous, for example NaOH aqueous plus HCl aqueous gives rise to NaCl aqueous plus H2O, water. Okay, in this reaction no gaseous components are involved. So for in such reactions delta H is equal to delta U, right, and for example if you take gaseous reactions, for example H2 plus Cl2 gives rise, H2 gas plus Cl2 gas gives rise to 2HCl gas. In this, if you calculate the number of moles of gaseous reaction, that is delta Ng, the change in number of moles of gaseous products. For example, gaseous products, how many number of moles of gaseous products? 2 minus number of moles of gaseous reactants, 1 into 1 plus 1, that is 2, that is equal to 0. So in case of gaseous reactions also delta Ng is equal to 0. In such case delta H is equal to delta U. Okay, so delta H is equal to delta U, delta H equal to delta U not only in the case of solids and liquids. Okay, in case of gases also delta H is equal to delta U, provided delta Ng equal to 0. Okay, for example, if delta Z is positive, delta Ng is positive. If delta Ng is positive, if delta Ng is positive, and if this value is positive, If this value is positive, then we can write delta delta H is greater than delta U, right. For example, if this value is positive, then we can write delta H is greater than delta U, and if this value delta Ng is negative, then we can write delta H is less than delta U. Okay. So, these are the two important cases, right. In case of delta Ng negative, this value can take the negative, delta Ng can take the negative value, that is delta U is more than delta H, that indicates, if this value takes the negative sign, that indicates delta U is more than delta H, right. So, these are the cases, right. So, what I want to conclude from this lecture is, heat absorbed at a constant volume is equal to change in internal energy, but most of the reactions are not carried out at constant volume, but most of the reactions which involves volume changes. So, the reactions in which volume changes takes place, energy changes are not equal to internal energy. So, for such cases, and in order to study such reactions, or in order to such cases, we have to introduce another function, that is enthalpy, and that function explains the systems or heat changes, heat absorbed at constant pressure, that is heat changes that are accompanying, or heat changes that are taking place at a constant pressure. Already we discussed that heat changes at a constant volume, but heat changes at a constant pressure is very important, because most of the reactions are carried out at constant pressures, not at constant volume, right. So, this is the only single point that you have to remember in your mind. Okay. And this enthalpy change can be measured by calorimeter, and that enthalpy delta H is equal to heat capacity of calorimeter, and change in temperature and molecular weight of the substance and mass of the substance. This is the formula to calculate the enthalpy change in a chemical reaction, and enthalpy change can be measured by a calorimeter with the formula, where C is the heat capacity of calorimeter, delta T is the change in temperature, molecular MW, this is the molecular weight of the substance, and M is the mass of the substance which is taken, right. So, this is about enthalpy. I hope you understand this lecture. Thank you for watching.